Hello, my wonderful AP chemists. Today we're going to talk about Le Chatelier's principle. So Le Chatelier said that if you have a system that's at equilibrium and you apply a stress to it, it's going to shift in the direction that minimizes that stress. So let's write that down first. When a system at equilibrium is subjected to stress, the system will shift in the direction that minimizes the effect of that stress. So what does that mean? So if your system is already at equilibrium, so the forward rate and the reverse rate are equal to each other, and then you stress the system. A stress could be a change in concentration, a change in temperature, a change in volume. So you're changing the conditions, and so your system is no longer at equilibrium, meaning the forward rate is not equal to the reverse rate anymore because you've stressed it. You've added too much heat, you've added too many reactants, something like that. So what will happen is the system will shift to the side that minimizes the effect of that stress. So if I add a lot of heat, so if it was already at equilibrium and I add heat, it's going to go in the direction that uses up that heat so that it doesn't affect it. And when we say it shifts, we usually say shifts right or shift left. What does that mean? It means that one of the rates is faster than the other rate, so it is no longer at equilibrium. So if it shifts right, that means that the forward rate is faster than the reverse rate until it reestablishes equilibrium, and then you get to a point where they are equal. If it shifts left, that means that the reverse rate is higher than the forward rate for a little bit until we get to equilibrium again. So let's look at this reaction here. We have nitrogen reacting with hydrogen to form ammonia. We have a delta H, so it's an exothermic process here. And we want to see how these stresses affect our system. So we're going to look at changes in concentration, pressure, volume, and temperature. Let's start with changes in concentration. So what if you're already at equilibrium, forward and reverse rate are equal to each other, and you add more nitrogen? Well, if you add more nitrogen, then now you have too much nitrogen. Remember, you have a certain ratio of products to reactants that you have constant at equilibrium. So if you add nitrogen, then now you have too many of the reactants. So what's going to happen is the system will shift to the right, meaning the forward rate is going to be a little bit faster in order to use up that extra nitrogen. So shifts right to use up the extra nitrogen that we've added. Okay, what if you add more hydrogen? Well, same thing. You have too many reactants now. You have too much hydrogen. So it's going to shift to the right. The forward rate is going to go a little bit faster to use up that extra nitrogen, that extra hydrogen. So it shifts right again to use up the extra hydrogen. How about if you add more ammonia? So you're already at equilibrium, everything's good, and then you add more products. Well, now you have too many products, you have too much ammonia. So which way would it shift to get rid of that extra ammonia? Well, it's going to shift to the left. So the reverse rate is going to be a little bit faster until it uses up that excess ammonia. So shifts left to use up extra ammonia. What if you add argon? It tells you it's inert. That means it doesn't really react. It just sits there. So if I add argon, what's going to happen? Nothing, right? It doesn't really affect anything. So no change. Let's add one more just for fun. What if you remove some ammonia as it forms? So I'm at equilibrium, my ratio is what it's supposed to be, and now I take away some ammonia. Well, now I have, I don't have as much ammonia as I need, right? So it's going to shift to the right to make up more ammonia. Shifts right to make more ammonia. So when you stress your system, it's going to shift to the side that will would minimize the effect of that stress. Okay, let's look at pressure. Now, pressure is only significant if it's because of a change in volume. So if the pressure is due to a change in volume, then it's going to shift your reaction. If the pressure is just because I added, like inert argon gas, for example, then there's not going to be any change. So the pressure only affects the equilibrium position if it is because of a change in volume. So what is pressure? Well, pressure is collisions of gas particles, right? So let's say I increase my pressure. I was already at equilibrium, everything was good, and I suddenly increase the pressure. That means I have too many collisions. Well, which side would it go to minimize the effect of too many collisions? Well, I have too many collisions. I'm going to go to the side with less gas particles so that I don't have as many collisions. So looking here, I have 4 gas particles on this side. I only have 2 gas particles on this side. So if I have too much pressure, too many collisions, then I want to go to the right to make more of this so that I have less pressure because I had too many collisions. So this would shift right towards side with less gas particles. Okay, what if I decrease the pressure? Well, if I decrease the pressure, then I don't have enough collisions. So I want to make more collisions. So I want to go to the side with more gas particles so that I make up for those collisions that I lost. And so that's going to shift to the left. Towards the side with more gas particles. So I get my pressure back up. Okay, let's look at a change in volume. So if I increase my volume, what's going to happen? Well, whether you have a solution or whether you have a gas, when you increase the volume, then you decrease the concentration, right? You have the same number of moles, but now you have it in a bigger volume. So your moles per liter, your concentration is going to go down. And so if it's not as concentrated, my concentration is going down, I want to go to the side with more particles so that my concentration goes back up. And so in this case, I have 4 particles on this side, and this applies to ions or gases. So I have more particles on this side than here. I have 4 here, only 2 here. So if my reaction is too dilute, I want to go to the side with more particles to make it up for that concentration that I lost. So this would shift left towards side with more particles. If I increase the volume, that means I've decreased my concentration. That's why it's going to go to the side with more particles. If I decrease the volume, make it take a smaller space, then I've increased my concentration. My concentration is going to be too high. So my substances are way too concentrated right now. So I'm going to go to the side that has less particles so that it's not as concentrated. So now I'm going to shift to the right side that has less particles. And again, with concentration, that applies to ions or gas particles. Finally, change in temperature. So in a change in temperature, it affects exo and endothermic processes differently. And you want to treat your heat as either a reactant or a product in this case. So if I increase the temperature, that means I'm applying more heat, right? So which direction would it shift to minimize the effect of adding more heat? Well, this reaction is an exothermic reaction. And so exothermic reactions release heat. So I'm going to write it as part of my product. If it was endothermic, then I would add my heat to my reactant side. And so I'm going to say, oh, I have too much heat. So which way would it shift to use up that extra heat? Well, it's going to shift to the left, meaning the reverse rate is going to be faster. So this one will shift left to use up excess heat. What if I decrease my temperature? Well, if I'm cooling it down, I'm removing some heat, then I don't have as much heat here. So how would I make up for that? Well, I want to shift to the right to make more heat. So shifts right to make more heat. So you want to treat your temperature, stress in temperature as adding more heat or less heat to the reactants or products. Okay, let's look at another example here. Here we have 2NO2 reacting together to form N2O4 and heat. So this one is also an exothermic process. Let's see, if you decrease the volume, what is going to happen? Well, if you decrease the volume, then that means that the concentration will go up. And so I want to go to the side with less particles so that I make up for that increase in concentration. So I have two particles here. I have one particle here. And so I want to go to the side with less particles to make for it. So shifts right to the side with less particles. Okay, what if I increase the pressure? And we're going to say here the pressure is due to volume. Because if I'm just increasing the pressure by adding like an inert gas or something like that, it's not going to change anything. So if I increase the pressure, that means I have too many collisions. So what do? I have too many collisions. So that means I want to go to the side with less gas particles so that I have fewer collisions. So that would be to the right. How about a change in temperature? So I'm decreasing it, so cooling it down, removing heat. So if I'm removing heat, I don't have as much heat here. So what do I do to make up for that? I shift to the right to make more heat. So all of these were shifts, right? Let's look at another example. So I have some protons here that I'm adding to chromate ions, and I'm forming the dichromate ion and some water. And these are a little bit trickier. They're not as straightforward. Let's look at addition of HCl. Well, at first glance, I don't see HCl anywhere here, right? But what is HCl? Well, HCl, if I'm adding it to the solution, because this reaction is happening in water, well, HCl in water ionizes to H pluses and Cl minuses. So I'm really adding H pluses and Cl minuses. So do you see H pluses or Cl minuses here? Yes, you do. You see H pluses right here. So I'm adding a reactant, basically. I'm adding extra H pluses. So which way would it shift so that it uses up that extra H plus? Well, it's going to shift to the right. Shifts right to use up the excess H plus. The Cl minus doesn't really do anything. It's not in my reaction. It doesn't matter. Okay, how about NaOH, adding NaOH? Well, at first glance, again, we don't see any NaOH here. But if I'm adding NaOH to my solution, then that's really the same thing as adding Na pluses and OH minuses. Do you see Na pluses or OH minuses? No, you don't see either one. So is there no change? Well, actually, no. Na pluses, I don't see that it can do anything to this, but OH minuses can. OH minuses can react with the H pluses to remove them, right? H plus and OH minus combine to form water. And so I'm basically removing the H pluses by adding the NaOH. So what do? Now I have too few H pluses, so it's going to shift to the left to make up more H pluses. So OH minus removes the H pluses. And so it's going to shift left to produce more H pluses instead of the ones that I lost. Okay, how about addition of NaCl? Well, I don't see NaCl here. If you add NaCl to a solution, that's really adding Na pluses and Cl minuses. I don't see any pluses or Cl minuses. I don't see anything that could react with Na plus or could react with Cl minus, so no effect. Nothing changes. Let's say no change. Okay, how about adding water? Well, some of you might say, oh, I see water right here. It's a product. So if I'm adding more water, it's going to shift to the left. Well, it does shift to the left, but that's not the reason. Remember, solids and liquids do not affect equilibrium. If I add more of my liquid or more of my solid, no change, right? And so it's not because I'm adding a product that it affects it. The reason why addition of water affects it is because when you add more water, you're going to change your volume, right? You're going to make things more dilute. I have all these ions swimming around in the water. If I add extra water, then my concentration goes down. That's why it affects the equilibrium, not because water is a product here, because that's a liquid, it doesn't affect the equilibrium. So what happens when I add water is my concentration goes down. So which way would you shift? You're going to shift, if your concentration is lower, you're going to shift to the side that has more particles. And so let's look at the particles here. I have 4 particles here, 4 ions. Here I only have 2 particles, and one of them is just an ion. So it's going to shift to the left because it has more particles on the left side. So be careful if you're asked a question like this. You might get it right to the direction, but if you're asked to explain, you don't want to say because you're adding more product there. Shifts left towards side with more particles. Okay, and then finally heating the flask. Well, it doesn't really say if it's endo or exo, so I guess it depends. So let's, for fun, say that it's endo, since we did a bunch of exos. So if it's endo, that means heat is right here. So if I am heating the flask, I'm adding more heat. Which way would it shift? It would shift to the right. to use up the excess heat. What if it was exo? So what if your heat was here? Well, if I'm adding more heat, now I have too much heat, so it's going to shift to the left to use up that heat. So when it comes to heat or cooling, it depends on if it's exo or endo. Okay. The very last topic of this chapter is how the value of the equilibrium constant K affected by different things. So we just saw that, you can change the equilibrium position for a while until the reaction goes back to equilibrium. But does the equilibrium constant actually change? The only thing that changes the equilibrium constant is a change in temperature. Concentration, catalyst, volume, none of that will change your K. The only thing that affects it is the temperature. And let's see why. So addition of reactants or products, no change in K. Well, why? So let's say that you have this reaction right here. And let's say I add, so my K is the concentration of B right over the concentration of A. Let's say I add more A. I increase A, right? So I've increased this concentration. Well, what's going to happen? Well, if I increase A, it's going to shift to the right to make more B. And so both of them increase by the same amount pretty much. And so your K remains constant. So if I change my concentration, my equilibrium constant will remain the same because my reaction will shift in the direction that makes up for the other one so that they both increase or both decrease by the same factor. And so K remains constant. Okay, what if I add a catalyst? Well, what does a catalyst do? A catalyst speeds up the reaction. So it's going to speed up the forward reaction. It's going to speed up the reverse reaction. It doesn't really change the concentrations of my substances. And so no change in K again. Speeds up both reactions equally. And so no change. Okay, what if I change my temperature? Well, then you're going to get a change in K. So let's think about this. It depends on if it's exo or if it's endothermic. So let's start with exo. I'll write it down here. So you have A to B, and it's exothermic, so you're getting heat here. Your K expression is the concentration of B over the concentration of A. Well, if I add heat, so I'm increasing the heat, which way is it going to shift? Well, it's going to shift to the left to use up that extra heat, right? So it's going to shift to the left to make more A. Did I make more B? No. In fact, I actually used up some B. And so in this case, my value of K is going to decrease when I increase my temperature. Well, what if it's endo? Let's see. So if it's endothermic, heat is considered part of the reactants. So K is concentration of B over the concentration of A. Let's say I increase my heat. So now I have too many reactants, too much heat, right? And so it's going to shift to the right to make more B. Did I also increase A? No, I did not. In fact, I used up some A to make B, right? And so in this situation, my K value increases. If you are cooling it down, obviously it's going to be the opposite. So this is increase in temperature. Let's look at decrease in temperature. So if I decrease my temperature here, so I don't have as much heat, which way is it going to shift? It's going to shift to the right to make more heat, right? And as it shifts to the right, it's going to make B and heat, so it's going to increase B. I did not increase A. In fact, I used up some A. to make B, right? And so my K would increase. So here K decreases, here K increases. In an endothermic process, if I decrease my heat, K is the concentration of B over the concentration of A. And so if I cool it down, so I have less heat, it's going to shift to the left, and it's going to make more A. It's not making more B, and so my K decreases. Here my K increases. So it's opposite the effect of the change in temperature on K, whether it's exothermic or endothermic. Now, just so you know, when you increase the temperature, we said K decreases here and K increases here. In reality, yes, it shifts to the right or shifts to the left, but in reality, when you increase the temperature, both forward and reverse reaction are actually increased, right? If you increase the kinetic energy, particles are moving faster and both rates are going to increase, right? It's just that the endothermic process will increase more. So if you read this, the process that needs heat in order to form is going to shift or go a little bit faster. So in here, let's say I increase my temperature, so I have more heat. The forward rate is faster and the reverse rate is faster, but the reverse rate is is faster at a higher rate. So my reaction still shifts to the left. The forward rate is faster, but the reverse rate is even faster, if that makes sense. So both of them increase, but the endothermic process increases more. All right, that is it for the chapter. Have a great day, guys.